James Webb Space Telescope discovered the impossible. A star with the energy output of an entire galaxy. Yet the paradox is that it cannot be seen directly. How is it possible that the matter it's made of neither emits or reflects light? What if Webb has, for the first time, observed not an ordinary star, but an object made of the very substance that makes up most of our universe? Today we journey to the edge of cosmic time. We'll explore how a star, powered by dark matter, could help solve some of astronomy's greatest mysteries. From the aftermath of the Big Bang to the birth of the first galaxies and the origin of supermassive black holes. What exactly are dark stars, and why do scientists believe they may have lit up the cosmic dawn? Along the way, we'll see how dark stars might connect an entire web of cosmic puzzles. Ultra-bright blue monster galaxies, the mysterious little red dots, and black holes that grew too big, too fast. Has JWST truly found evidence of stars made of dark matter? Or are we just witnessing something even stranger? Let's find out. Our story begins at the dawn of time. The universe was born in the Big Bang, a hot, dense fireball of energy. As it expanded and cooled, protons and electrons combined to form the first atoms of hydrogen and helium. About 380,000 years after the Big Bang, the cosmos became a dark, blank slate, filled with a diffuse hydrogen-helium fog. Then gravity began to take over. Over millions of years, the once uniform gas slowly thickened under its own weight. This era is known as the Cosmic Dark Ages. There were no stars yet, only gathering clouds drifting through an ever-expanding night. At this point, however, cosmologists ran into a mathematical puzzle. Pure hydrogen and helium do not easily form stars. They remain hot and resist collapse. According to basic models, the gas of the early universe should not have condensed into stars as quickly as it apparently did. And yet, just 300 to 400 million years after the Big Bang, telescopes have detected bright objects and emerging galaxies. What triggered the birth of the first stars so early, when conditions seemed so hostile to their formation? Something was missing from the models, an extra ingredient that could give gravity an additional push. This is where dark matter enters the picture. Decades before JWST, astronomers discovered that this invisible mass dominates the cosmos. Galaxies rotate too fast at their edges, and clusters of galaxies are held together by far more gravity than visible matter alone can provide. An unseen form of matter, dark matter, acts as the universe's gravitational glue. In the early universe, dark matter's influence was decisive. It clumped into dense halos long before ordinary gas could, creating powerful gravitational traps. When primordial gas fell into these dark matter halos, it could condense far more efficiently, ultimately igniting the first stars in places where they otherwise could not have formed. This invisible framework effectively jump-started the process of cosmic structure formation. The idea of dark matter dates back to the 20th century. In the 1930s, Fritz Zwicky noticed missing mass in clusters of galaxies. In the 1970s, the work of astronomer Vera Rubin on spiral galaxies confirmed that some invisible substance, dark matter, makes up about 85% of the universe. Today, we're confident that ordinary matter, the stuff that makes up stars, planets, and people, accounts for only a small fraction of what exists. Dark matter neither emits nor absorbs light. We infer its existence solely through its gravitational effects. The leading theory suggests it consists of a new type of particle, often imagined as WIMPs, or weakly interacting massive particles. If WIMPs exist, they would be heavy, slow-moving particles that interact through gravity and possibly the weak nuclear force, but not with light. Crucially for our story, many WIMP models predict a fascinating behavior. When two dark matter particles collide, they can annihilate, converting their mass into energy. Something like a tiny matter-antimatter explosion. In today's dilute universe, such collisions are extremely rare. But in earlier, denser epochs, they may have occurred frequently enough to produce real astrophysical effects. All of these ingredients set the stage for a radical hypothesis. What if, under the right conditions, dark matter could not only help stars form, but actually power them? In 2007, physicist Catherine Fries and her colleagues proposed a bold idea. The very first stars may have been powered not by nuclear fusion, but by the annihilation of dark matter. And they called these objects dark stars. The name is somewhat misleading. These stars would not be dark at all. In fact, if they exist, they would be among the brightest stars ever formed. Their energy source, however, would be dark matter concentrated within them. Here's how it might work. Imagine a newborn protostellar cloud a few 100 million years after the Big Bang. Normally, as a gas cloud collapses under gravity, it heats up. If it becomes dense enough and hot enough, around 10 million degrees, hydrogen nuclei begin to collide and ignite nuclear fusion. Voila, an ordinary star is born. But in regions that are rich in dark matter, something different could happen. As the gas cloud contracts, it drags dark matter particles along with it. Dark matter cannot cool by emitting light. It's invisible, so it tends to linger in the core. There, dark matter particles can become so concentrated that they begin to annihilate with one another. This annihilation releases a stream of kinetic energy and particles that heat the gas from the inside. If the heating from dark matter becomes strong enough, it counteracts gravity. The collapse of the gas cloud halts before reaching the extreme densities required for nuclear fusion. Instead, the cloud stabilizes as a giant, puffy mass of hot gas, with dark matter annihilation acting as its heat source. In essence, dark matter behaves like a burner beneath a hot air balloon, inflating the star. The result is a dark star. Though in reality it isn't dark at all, but rather an enormous, relatively cool by stellar standards, glowing object. No fusion furnace ignites in its core, yet the star shines brightly thanks to a continuous supply of energy from WIMP annihilation. According to Fries' models, a dark star would look nothing like the stars we're familiar with. Instead of a small, dense sphere like our Sun, it would be extremely bloated and diffuse. The numbers are staggering. Early calculations suggested that dark stars could swell to a radius of about 10 astronomical units, 10 times the distance between Earth and the Sun, roughly the size of Saturn's orbit. As Catherine Fries put it herself, they're big, puffy beasts. Inside this inflated volume would be mostly hydrogen and helium, the same primordial ingredients to any first-generation star. Perhaps only 0.1% of its mass would consist of dark matter. Yet this tiny fraction wields enormous power. The annihilation of those particles provides an energy source far more potent than nuclear fusion. A fully formed dark star could shine 1 to 10 billion times brighter than the Sun. In effect, a single dark star could rival the brightness of an entire small galaxy. Unlike ordinary stars, which have a limited fuel supply and a fixed mass, dark stars could continue to grow. The heat from annihilation gently supports the star without blowing it apart, and its relatively cool surface means it does not emit the harsh ultraviolet radiation that would otherwise drive surrounding gas away. Matter keeps falling in. As long as the dark matter fuel continues to flow and annihilate, the star can accrete surrounding hydrogen and helium almost without limit. Calculations suggest these stars could grow to millions of times of the Sun's mass. Compare that to ordinary first-generation stars, population 3 stars, which are thought to reach at most a few hundred solar masses. In this scenario, a dark star would be in a league of its own, a true cosmic leviathan. This growth, however, has a dramatic endpoint. Eventually, dark matter annihilation must slow down. The WIMPs are either used up or dispersed as the star's core evolves. When this happens, the dark star can no longer support itself. After perhaps millions or even billions of years of shining, the star would rapidly contract and collapse. Without a fusion core or dark matter heating to hold it up, a supermassive dark star is expected to collapse directly into a black hole. Crucially, that black hole would inherit an enormous mass. Instead of the usual black hole seeds of 5 to 100 solar masses left behind by ordinary stars, a dark star could produce a black hole of hundreds of thousands or even a million solar masses in a single step. Suddenly, we have a potential answer to one of astronomy's most vexing questions. How did supermassive black holes in the universe grow so big, so fast? More than a decade and a half later, when JWST opened its infrared eye in 2022 and began observing the cosmic dawn, astronomers were stunned. In the first deep surveys, such as JADE's, JWST revealed galaxies that should not have existed, at least not so soon after the Big Bang. Some of these objects earn the nickname blue monsters because they're extraordinarily bright and blue, a color that signals intense star formation with very little dust, and they're also extremely compact. These galaxies were already shining at a time when the universe was only a few percent of its current age. Equally puzzling was JWST's discovery of tiny, faint red objects dubbed little red dots, which appeared around the same epoch. Unlike typical young galaxies, these dots showed no clear signs of active black holes, leaving their true nature uncertain. Then came the black holes themselves. JWST detected quasars, galaxies powered by actively feeding black holes at record-breaking distances. In some early galaxies, the central black holes appeared overly massive, reaching hundreds of millions of solar masses when the universe was only about 500 million years old. Standard physics struggles to explain how a small seed black hole could have grown into such a giant in such a short span of cosmic time. One striking example is the distant galaxy, UHZ1, observed at a redshift of about 10.1 to roughly 13.2 billion light-years away, at a time when the universe was only about 3% of its current age. UHZ1 hosts a quasar, a supermassive black hole actively accreting matter that could not have been seeded by ordinary stars given its enormous mass and the very limited time available for its formation. Cases like UHZ1 raise a provocative question. Were some black holes born already enormous? These discoveries shook the foundations of early universe theory. Taken together, the blue monster galaxies, early overmassive black holes, and little red dots point to serious gaps in pre-JWST theories, writes Cosmin Ilai, who later led research on the topic. It's as if JWST had discovered a bustling city where our models predicted an empty field. Astronomers rush to explain these anomalies. Could our galaxy formation models be missing some key physical processes? Perhaps the first stars form more efficiently than expected, or some exotic mechanisms accelerated early growth. This is where the dark star hypothesis emerges as an intriguing possible solution. Remarkably, many of JWST's early mysteries could be explained by dark stars. Blue monster galaxies, even a few dark stars forming within early protogalaxies, each shining as brightly as an entire galaxy, could make a young galaxy appear anomalously bright and blue, since the light from the dark stars is thermal and not yet processed by dust. Little red dots with no X-rays? A single dark star or a cluster of dark stars in the early universe could appear as a compact red object due to distance and relatively cooler temperatures. And because it's a star, not an accreting black hole, it would not produce X-ray emission. The enormous black holes, like the one in UHZ1, could be the direct remnants of dark stars. A dark star collapsing into a black hole with a mass of 1 million solar masses instantly provides a heavy seed, which could then grow into the billion solar mass quasars we observe just 600 million years after the Big Bang. In fact, recent work by Ilai and Friese demonstrates how UHZ1's quasar might have been seeded by the collapse of a dark star, offering a pathway to explain many of the impossible objects in the early universe. However, extraordinary claims require extraordinary evidence. The idea of stars powered by dark matter, while elegant on paper, naturally attracts healthy skepticism. Can we really see dark stars in JWST images? Or are there more mundane explanations? In 2023, Friese, Ilai, and their colleagues reported 3 particularly intriguing JWST detections as dark star candidates. These objects were initially cataloged in the JADE survey as JADE's GS-Z11, 12, and 13. Galaxies at redshifts of roughly 10 to 13, meaning we see them as they were just 330 to 400 million years after the Big Bang. To JWST's cameras, they appeared as tiny reddish spots indistinguishable in shape from point sources. At first, astronomers assumed they were early galaxies. What else could they be? They were bright for their distance, but not implausibly so for a galaxy. However, upon closer analysis, these objects began to match predicted profiles of supermassive dark stars remarkably well. The team conducted detailed modeling of what dark starlight would look like at such distances. They used a stellar atmosphere code called T-LUSTY to simulate spectra of hypothetical dark stars with various masses and temperatures, then compared these models to JWST's photometric data. The result? Each of the 3 mysterious objects had a spectral energy distribution consistent with a single supermassive star with a cool surface. Exactly what was expected for a dark star, rather than an entire galaxy of millions of hot stars. In fact, the match was surprisingly good. One candidate, JADE's GS-Z13, was best described as a dark star with a mass of around 10 to the 7th solar masses and a luminosity 10 billion times that of the Sun. The others fell into a similar range. These inferred masses and brightnesses line up precisely with the upper limits predicted by dark star theory. In short, if dark stars exist, these objects look exactly like what we would expect from supermassive dark stars. Another clue came from their appearance. At such distances, roughly 13.5 billion light-years, JWST's resolution is limited. It cannot clearly distinguish an object a few hundred light-years across from a pinpoint. The candidates appeared unresolved, meaning they could plausibly be single stars. If they were galaxies, JWST might have detected them as slightly extended spots. The researchers noted that JWST showed no extended emission that would require these to be galaxies. They could genuinely be individual star-like objects. Encouraged by these hints, the team called these three objects the first dark star candidates. The announcement caused a stir. If confirmed, it would be a historic discovery. The first stars composed of dark matter. Naturally, scientists outside the team reacted cautiously. Could these points really be dark stars rather than unusual galaxies or something else entirely? This is where the spectroscopy comes into play. Fortunately, JWST can do more than just take images. It can also split light into spectra. The JWST program obtained spectroscopic redshifts for these objects, allowing astronomers to precisely measure their distances. The initial spectra were low resolution, but they provided a crucial test: galaxy versus star. The combined light of a galaxy usually shows emission lines, bright spikes from hot gas, such as interstellar nebula, growing at specific wavelengths. A single star, on the other hand, primarily exhibits absorption lines, dark impressions where atoms in the stellar atmosphere absorb light at particular colors. In practice, identifying a single star at a distance of 13 billion light-years is incredibly challenging, but certain features can tip the scales. In December 2025, a follow-up analysis reported an exciting discovery. Signs of a helium absorption line were detected in the spectrum of JADE's GS-Z13. Another candidate, JADE's GS-Z14, a similar object from the same survey, had previously shown a comparable helium feature. Helium absorption is exactly what you would expect from a stellar photosphere, especially from a very hot, massive star. It's certainly not what you would see in a galaxy, which would more likely display emission lines from hydrogen clouds. While the data are still preliminary, this is the first direct spectral hint that at least some of these points are star-like in nature. The distinction is subtle, but extremely important. If JWST spectra ultimately confirm the presence of strong absorption lines and the absence of emission lines, it would clearly indicate we are looking at a single supermassive object, a star, rather than a cluster of stars in a galaxy. Essentially, this is the fingerprint of dark stars. Meanwhile, the team eagerly awaits additional data. Perhaps deeper JWST spectroscopy or the discovery of more candidates to obtain irrefutable evidence. The dark star hypothesis is thrilling, but standing at the edge of the known, skepticism is unavoidable. Many astrophysicists emphasize that extraordinary claims require extraordinary evidence. Are we truly seeing dark stars or unusual galaxies? After all, galaxies can be small and extremely bright if, for example, they're experiencing a burst of star formation or host an active black hole. Some researchers suggest that the high luminosity of these candidates could be explained by population 3-star clusters, groups of normal first-generation stars that are very massive and hot. Others propose that gravitational lensing could be at play. While the survey fields were carefully chosen to avoid strong lensing, subtle magnification effects cannot entirely be ruled out. The truth is, at such distances, our data is still very limited. So far, we have only photometric measurements and a few spectral lines from JWST. Without more detailed spectra or additional signatures, it's difficult to be certain. Even Frisi and Ilai acknowledge that these are only candidates. It's tantalizing, but unconfirmed. Nevertheless, the story's far from over. It's only just beginning. Some healthy skepticism also comes from particle physics. Despite decades of experiments, we have yet to detect dark matter particles on Earth. If it turns out that WIMPs do not exist, for example, if dark matter is something like axions or primordial black holes, then classical dark stars, as described, would be taken off the table. However, the very fact that JWST hints at something gives new experimenters another target. If these objects are indeed dark stars, their properties could help reveal the nature of dark matter itself. Let's take a moment to imagine that the dark star interpretation is correct. What would it mean for science? The implications would be enormous. First, it would be direct evidence of dark matter's role in the cosmos beyond gravity. For the first time, we would see dark matter through its thermal effect on stars. This could open an entirely new window into particle physics. By studying dark stars of different masses and ages, if we can find a population of them, we could infer properties of a dark matter particle, such as how effectively they annihilate, which relates to their cross-section and mass. In essence, the universe itself becomes our laboratory, and dark stars are our experimental apparatus for dark matter physics. Second, as we've discussed, dark stars elegantly resolve several cosmic mysteries at once. Blue monster galaxies, little red dots, and early quasars with supermassive black holes all suddenly make sense. In one stroke, our standard model of the cosmic dawn gains explanatory power over phenomena that previously seemed impossible. Third, confirming the existence of dark stars would give us insight into the very first generation of stars. We've long wondered about the transition from the Dark Ages to the era of light, the cosmic dawn. These giants could have delayed the onset of ordinary star formation by consuming gas, or accelerated reionization in certain regions thanks to their enormous power. They would also suggest that population 3 stars powered by nuclear fusion weren't alone. The early universe could have been a mixture of fusion-powered stars and dark matter-powered stars, coexisting or forming sequentially. So, what do we have? On one hand, a compelling theory, some intriguing data, and numerous striking coincidences between predictions and observations. On the other hand, caution, alternative explanations, and the reminder that nature often surprises us, even when we think we've anticipated every twist. The frontier of the cosmic dawn still holds its secrets, and only by looking deeper can we hope to unravel them. Future observatories such as the upcoming Nancy Grace Roman Space Telescope may detect dozens more high redshift point sources or reveal subtle details in their light. If dark stars do exist, hidden among galaxies, the next decade of observations is likely to uncover them. Clearly, introducing a completely new class of objects is a major step. But that's how science advances. We venture into the unknown and sometimes encounter surprises that force us to update our cosmic inventory. If real, dark stars would be a spectacular addition to that inventory.